one, he told me last week his program only required pre-calculus algebra, and he hadn't had any trig since high school and forgotten most of it. So we were having to have a 20-minute refresher on trigonometry between classes. It took all the time I had. Okay, we'll go from current slide, and this is where we get. First, can't think of any special announcements or anything coming up. Any questions from you? Anything we've done so far? Any questions at all? All right. Oh, there was a question now I remember Patrick asked, how far are we going on 7.5 before the test? And like I was telling him, first time I've taught from this text, so I'm guessing as engineers, y'all are probably going to need moment centers of mass centroids and stuff, aren't you? Or do you, what you think? Say again? You won't need it, huh? Yeah. You didn't? Okay, so I would say then probably, let me just see, because, I mean, it's a pretty good section, but it's a long one. But then fluid pressure, I think you'll need that one. So that's 7.7. Yeah. So I think what we'll do 7.4, which is what we're working on now. 7.5 work, I think you'll need that one for physics, if nothing else. You probably will need moments centroid, but the odds are, if and when you need it, you're going to have it in that course. Statics and dynamics, they use that a lot. And most engineering, or at least back when I was in college, all engineering majors took those. But I think you'll have everything you need for that. So we may skip 7.6, move on to 7.7, and that will be the last section then before, and we'll do that. So to answer your question, we'll finish 7.4, 7.5, and 7.7. Okay? And these are fairly short sections. I hope they will be. The centroid one was the long one, which was good stuff, but what we might do is a quick PowerPoint show, but not have any problems you have to do. Okay. Now, we did do last time the definition of arc length. Does anyone remember what that was? No, it was a long time ago, a very long weekend. Does anyone remember what your integral, these are applications of integration, the integral for the arc length is? Usually given the symbol S, that's almost standard for arc length, and this will be the integral. Now it can be either in x's or y's, just depends on which one it is. Given you have a function, the arc length will be from, I'll do it in x. X equals some value a to x equals some value b. If it's y, they usually use c's and d's, whatever that is. You don't have to put the x there, but I'm putting that for a reason. Okay? So therefore, your incremental amount has got to be your dx, if that's going from x. dy's if those are c to d. Okay? Now, remember, the arc length is approximately the Pythagorean estimate of the things between the 2 points, okay? Which would normally be delta x and delta y's, but we're going to divide delta y by delta x and bring a delta x outside, and that's where the dx comes from. So that leaves us where there was a delta y, x is a 1, and the delta y is going to be your f prime of x squared, okay? Because Pythagorean theorem, that would be the square root of delta x squared plus delta y squared, and then we're going to divide that by delta x squared, which brings the delta x out here, and that'd be a 1 plus dy dx squared, okay? And that's where your y comes squared. If this were y's, then it's c to d, g prime of y dy. Okay, so that's the only difference. So there's your arc length function. Okay. So let's do the one they have here. Find the arc length from x1, y1 to x2, y2 on the graph of f of x equal mx plus b. Okay? Now, I like to sort of get into a pattern. I hate memorizing things, but I like patterns. Okay? So the first thing you've got to do here, if that's your f of x, what's the first thing you've got to do? Take a derivative. Back in Cal 1, that was always a good answer to give, right? Okay, so let's do what is f prime of x. If there's your f of x, what's f prime of x? M. You're absolutely right. Woo. Okay, well then what's the next thing you got to do is square that. So what's f prime of x squared? Pretty easy. M squared. Okay? Now the next thing we got to do is take a square root of that. The square root of 1 plus f prime of x squared would be the square root of 1 plus m squared. Okay? So it's the integral from a, oops. In this problem, what would be corresponding to your a? Your x1. From x1 to x2. That's your a and your b. Okay? From x1 to x2. Now, what's the square root of 1 plus m squared? That's a number. Whatever your m is, that's just a number. That number could come on the outside. So let's do 1 plus square root of 1 plus m squared on the outside here. And all you've got on the inside is a dx. And what's the antiderivative of dx? Get out of there. Okay. Square root of 1 plus m squared. Antiderivative of dx. X. Okay. Evaluated from x1 to x2, which would be the square root of 1 plus m squared times x2 minus x1. Whoa, that's a 2 up down there, not a 2 up there. Sorry. Okay. Now, I can't think of anything else to do to that one, but it's such a, in some ways, a very simplistic type problem. Because it's just a straight line. Okay? Now, if I were to graph that, whoa, if I could get my pen back so I could graph that, okay? If there's my graph of y is equal to mx plus b, where this is b, your slope is m, okay, and you're going from x1 to x2. What your, let's just pretend that does that. What you got there is a trapezoid, right? And the trapezoid is 1/2 the base times, yeah. I was thinking of doing it this way. Going to try to make it a bit more geometric. Oh, I see what they do. let's figure out what m is. If you're going from this point to this point, what is your m? What we did was correct. They just lost the m, okay? What is the m then? y2 minus y1 over x2 minus x1, okay? Because that's just a straight line. That's the slope. It's that slope everywhere. So we'll take that and plug it in here. That's the square root of 1 plus y2 minus y1 over x2 minus x1 squared, right, times x2 minus x1, okay? Well, if you multiply that through the radical, that would be that thing, the square root of that thing squared, right? That's the same thing, right? x2 minus x1 is the same as the square root of x2 minus x1 squared, right? You square it and take a radical. Multiply that across, and you have the square root of x2 minus x1 squared. But here, it cancels out, and that would just be plus y2 minus y1 squared, which is the line from this point to that point. Okay, that is your distance formula, which of course is what you got, because that is a straight line between the two points. Now, to me, that other answer is just as good. This is a little longer to write, but maybe it makes more sense this way to say, oh, that's just the distance between here and here. Times, okay, okay. Well, it still wouldn't be the area. No, that's the arc length. Oh, that's what we're looking for, arc length. The distance between, not the area under here, the arc length. That's just that distance there, which of course it is. That's what a straight line is. That's the distance formula tells it to. So I guess that does make sense to carry it that way then. So a bit almost too simple of an answer. And by the way, I can't remember if I mentioned it or not. You have a little blurb on this page on Christian Huygens. Did we mention him before? Dutch mathematician. He invented the pendulum clock. And James Gregory, which you don't hear nearly as much about, a Scottish mathematician, both made early contributions to the problem of finding the length of a rectifiable curve. Okay, Huygens you'll see in other places. I've never really run into Gregory that much, so either of those would be potential paper topics. Okay. Now, trying to see if that little blurb at the bottom would make any difference. Let's see how they do it, which I think is pretty. They just start off differently than I did. They start off figuring out what that, well, the f prime is m, which of course would then be y2 minus y1 over. See, I just started with m from the formula. They went on and did this from step one, okay? And then it follows from that, since that is your slope, that would be the square root of y squared minus y1, y2 minus y1 over x2 minus x1 squared, okay? And that under the radical, if you, let me get your, Corbin? Okay. Anyone else come in since they're called roll? I got you. I will have to watch for you. You sneaking around. Okay. All right. So they just started from it this way rather than the way I did. That's still the next step is to write that over the same denominator, which would be x2 minus x1 squared over x2 minus x1 squared with the 1 here. that gives you this plus that all over this. That's all a constant. Integrating the dx just gives you the x evaluated from there. So that gives you an x2 minus x1 there. And since this square root of this perfect square is just that, you can pull that out and just have those then divide away, which I assume they did without showing you they did, and that's how they get it. And again, this is a very simple example, and they're showing something that's sort of patently obvious, so it's kind of almost seems like they're confusing the issue, making it simple. I don't know. Which is the formula for the distance between the 2 points, which would be that arc length. Okay? Formula for arc length for a straight line is the standard distance formula. So that's what they're trying to show, then simply just to say this is what it is. Okay? But that was example 1, right? Yeah. They're skipping examples 2, 3, 4, and 5, okay, which of course they showed the very easiest one they had and skipped the rest of them. So let's go back and pick those up here, okay. Any questions on that? I know that was sort of a lot of blah, 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 but here's one. Find the arc length of a graph of this one. Y is equal to x cubed over 6 plus 1 over 2x on the interval 1/2 to 2, okay, as shown in the figure. And of course they don't show the figure. They're doing the text but not on the slide set, which I wish they did. So we're finding arc length between that. That is, by the way, how do you say this? It's, you could sort of rephrase this as, least common denominator here would be 6x, and the first part would then be a x squared plus goodness, my brain's not working too well. 3 plus 3, I think it would be, over 6x. Okay? A rational expression, as long as you don't get anywhere close to 0, where you have a vertical asymptote, you're going to be okay. Okay? So, that's why they gave you an interval 1/2 to 2. You can't include that 0 there because 0, it blows up, and you can't do it. You have to be some interval on which that is a continuous function. And that would be perfectly fine. Okay? Picture in the book shows you how it looks. Not a very common curve at all. Okay. Now, what are some things you're going to need to do to find that arc length? Remind me, what is the arc length? What's the formula for it? And you're doing dx's here because you've got y as a function of x. That'll be what? Integral from? And what are your a and b's here? 1/2 to 2, okay. Square root of 1 plus, okay, I'll write it as y prime squared dx. Okay, you could write f of x prime, which is fine, but since they gave it to you as y, I'll just write it as y prime. Y'all are okay with all these different notations for your derivatives, right? You write dy dx squared, you could do just about anything. Okay? Now, so what's the first thing you're going to have to do? Take a derivative. Okay? You got to get the y prime. So what is your y prime? Now, when I go to do one like this, I like to rewrite it in exponential notation, not rational notation or radical notation, exponential. And that would be x cubed over 6 is perfectly fine. What would be the second part? How about a 1/2 x to the -1. Okay. That, to me, is far easier to take a derivative of that form than of a quotient form. Now, if y'all love the quotient rule, go for it. Knock yourself out. To me, so much easier to get it into exponential notation, and then it's pretty easy to do. So what's its derivative? Y prime is equal to? (1/2) x squared. I'll buy that. Minus 1/2 x to the -2. I'll buy that. Okay? And since that looks like it's begging to factor out the 1/2, I'll do that as well. And what does that give you? X squared minus x to the -2. I don't need brackets, parentheses would have been just as good. But that's the next thing I've got to do. Square it. So y prime squared then would be, help me. Okay, I'm going to put the 4 in the denominator. Help me. X to the 4th minus what? Okay. I won't quite agree with that either. Let's foil it. Well, no. Yeah, we're squaring that, so that'd be x squared minus x to the -2 times x squared minus x to the -2. I'll agree the first term is x to the 4th. What's the next? You said a minus. I'll agree at the end you got a plus x to the -4. That's why I wouldn't quite agree with minus. Okay? But what you got in between? This times that, or plus that. 2. That's all. 2, because x squared over x squared is 1. So that's what your product is. Okay? Now, next thing I'm going to do is add 1 to that. Right? Alright. So 1 plus y prime squared would be, I'm going to add this as 1 is 4/4. Are y'all okay with that? 1 is 4/4, right? So that would be x to the 4th. And here we have a -2 over 4 plus 4 over 4 would be plus 2 over 4. I'll get the 4 in there in a minute. Plus x to the -4 over 4. Do you agree with that? Okay. What I did, in adding 1 to this, I added 4/4 to it. And it doesn't change this or that, but 4/4 plus minus the 2/4 would be a positive 2/4. Now left it in this form because guess what the next thing is? Take a square root of it. So let's take a square root of this and a square root of that. Okay? Well, this is going to be what's going to be in here. What we have here, I know, is going to be a 1/2 out front, right? Because I can take the square root of 1/4, 1/2. And then we got the square root of that thing. Anyone want to hazard a guess what that might be? Especially since we squared this to get that. Guess what we can square to get this? Yes, make that a plus. X squared plus x to the minus 2. Try it. You'll like it. See if it works. Again, recognize patterns probably more than other things. This thing right here is because this is the perfect square of this. This with a plus in it is going to be a perfect square of it. All right? You buy that? Okay. So this will be the square root of this perfect square, x squared plus x to the minus 2. All right. That's what my radical is. So let's do this. S is equal to the integral from 1/2 to 2 of, pull that 1/2 out front, x squared plus x to the minus 2 dx. And if I'm not mistaken, we can probably do that antiderivative pretty easily, can't we? Or at least do it. What would that be? Antiderivative of x squared. X cubed over 3 plus antiderivative of x to the minus 2. X to the minus 1 over minus 1. So I'll just leave. I did away with that. Okay. The minus sign made it a plus. Okay. Which would be 1 over x, right? Alright. So let's rewrite that as 1/2 x cubed over 3 minus 1 over x. Evaluate that from 1/2 to 2. Okay? Don't forget the 1/2. Okay, plug and chug. What do we have here? When x equal 2, what's that first term? What's that? Did I hear 8/3? I thought so. Okay. 8/3. Okay. Minus 2 plugged into 1 over x. Plug in the 2 for the 1 over x. 1/2. Okay. Okay, now minus plugging in the bottom part. So that's going to be a minus here. And that's going to be 1/2 cubed. 1/8 divided by 3 would be 1/24, right? Do you buy that? Yay or nay? Okay. Then minus a minus is going to be a plus. And 1 over 1/2 is the same as 2. All right. Now, I don't know the best way to go from here. The rest of it is just math, okay? Fractions math at that. So what I would be tempted to do, 1/2 of 8/3 would be 4/3 minus 1/4, right? Minus 1/48 plus 1. I'm not sure that's any better, but at least it got rid of the 1/2 out front. So I think what we have to do is least common denominator of 48 and multiply and divide by that. Yuck. 3 will go into 48 16 times, right? 16 times 4 is 64 48, so I'll wait and put my 48 at the end. 4 will go into 48 12 times, so that's minus 12. Is that right? Minus 1 plus 48. Boy, that's ugly. Okay, all over 48. Okay, well, 48 and 64 is 110, right? Minus 13 would be 97. Is that right? Second? Oh, you're right. I can't read my writing. Yeah, it's 112. 112 minus 12, so that'd be 99 48s? Is that what you're getting at? Okay, I don't think, yeah, there's a common factor there. 3 will go into both of those. That would be 33/16. Is that reducible? I don't think so. And I can't remember this guy. It seems like I've seen him before. Oh, I know you're in here too. There you are. Yeah, that's right. Jeremy, that's right. It's coming back to me now. Okay. 33/16. Oh, yes, that's what they got too. The hardest part there is the fractions. I mean, the integration is really the easiest part. Setting up to do your integration, that's probably pretty, you have to be careful with that as well. But if you remember what I said to begin with, or sometime last time, to do these to get problems that work, that means you have to find the function whose derivative squared added to 1 gives you a perfect square. Otherwise, you got a mess on your hand. And that's why they chose such a weird looking function as, there. Now it's easy to read. Weird looking function is this one. Because that one is 1 whose derivative squared plus 1 happens to be a perfect square. Okay? Yeah, it's going to be weird looking. And ultimately leads us to pretty weird numbers. Especially since you chose a fractional endpoint as well. Or they chose for you. But you see how that works. Frankly, finding arc length is usually not a very easy process. In reality, you're going to go to numerical integration just about. In the real world, very seldom will you have functions that happen to work out perfectly like this, or okay like this. Okay. All right, to erase, anyone need it up there a little longer? Okay, if you could even follow it. Okay. So let's go to example 3. Okay, example 3 is find the arc length of the graph of y minus 1 cubed equal x squared on the interval from 0 to 8. Okay, as shown in the figure. Okay. Now, I'm sure there must be some reason, because the last problem and this problem they put the interval as a closed interval, just like here. Whereas the arc length's not going to matter whether you add that point or that point at all. It's going to be the same if it was an open interval, okay? So I don't see any real reason they specify the closed interval, but it's okay. We can do that, okay? Now, if you look at the graph that they drew there, that's just a little portion of this, because frankly, is this even a function? No. For two x's, you're going to get the same y's if they're plus or minus of each other. That's not going to matter. So a plus 2 or a minus 2 is going to give you the same result here. So that by itself is not a function. So we hope that we're just going to deal with it on that interval. How would we go about, what's the first thing you're going to need for that? Anyone remember? We did it just a couple minutes ago. First thing you're going to need is? Second? Yes. Of what? Why? Why not? Okay. Now, anyone want to perhaps solve that for y and then take a derivative? Would that be your approach? Y'all are hardworking people, okay? What's an easier approach? Remember implicit differentiation? That's the way to go here. Implicit differentiation. Anyone not remember what that's like? Second? You do not? Yeah. Okay. All right. Here's what we're going to do. It's a chain rule type thing. Okay? Let's take the derivative of this with respect to x. Okay? Now that is a function of a function of a function. Y is a function of x, and y minus 1 is a function of x, and y minus 1 cubed is a function. Okay? So where do we do that, say, chain rule wise? What would be the first derivative you would take? Taking the derivative with respect to x of the left-hand side. What would that be? Okay, not yet. Let's wait and get there. First thing, let's take the derivative of the outermost function, the cubing function. That would be 3 times y minus 1 squared, then times the derivative of the inner function, and that would be y minus 1. Well, that's just going to be dy dx. Okay, so that's going to be, do you like to write it dy dx or y prime, or how do you want to write it? I don't care. Okay, I want to write y prime. I do care, okay? I'm just going to do it y prime because that's what our formula usually looks like too, isn't it? Okay, are you okay with that? Okay, derivative of the inner part is just y prime. Okay, now let's take the derivative with respect to x of the right-hand side. What would that be? This is really hard. 2x, okay, good deal. Now we want to solve for y prime. Okay? So what we're going to have to do that? Solve for y prime. Second? Subtract, you said? Divide. 3y minus y squared, y minus y squared, 1 squared. Divide that on both sides. Okay? And that will wipe that out. There's your y prime. Y prime is equal to 2x over 3 times y minus 1 squared. But we've still got a problem, don't we, Houston? That is a derivative, but we now need that. We don't need that inside our integral. Okay, we need a function of x. pain in the neck. If that were, say, a squared, that would be okay to do, but it is. It's a cube. But what you could do, I guess is what we're going to have to do, is at least partially solve this for y. So if you take the cube root of both sides, that would be y minus 1 is equal to x to the 2/3. Would you buy that? Take the cube root of both sides of this original equation, right? Now, if you square this side, y minus 1 squared, that would be x to the 4/3. Do you buy that? No. Yeah. Yeah, you double that. Right. Yeah or nay? Or is it all magic? Is that right, algebraically? What you think? You okay with it? Okay. So then let's change this to 2x over 3, and that times x to the 4/3. Okay. I think we can improve on that a little bit. Would that not be 2 over 3x to the 1/3? Now, maybe you'd have gotten there the same way if you'd have done the same type of thing before. Let's see. Y minus 1 is equal to x to the 2/3 power, and y is equal to x to the 2/3 minus 1. Yeah, we'd have been better to do that way, okay? Then y prime would equal 2/3 x to the minus 1/3. Yeah, we'd have gotten there a lot quicker had we done it that way. Sorry, took us on a wild goose chase. That just happened to be these are simple enough formulas. That would have been the way to go. So anyway, we got there two ways. 2 over 3x to the 1/3. Okay. So all that work for nothing, huh? I mean, for fun. Okay. Let's just erase all this. But you got to review implicit differentiation, didn't you? That was worth it. Yeah. Okay. We got our y prime. Okay. What's the next thing we got to do? Not quite. One step before that. Square it. Okay. So what's y prime squared? Help me, it's not that bad. What you got? 2 squared is? 4. Okay, really confident here. 3 squared is? 9. X to the 1/3 squared is? Okay, isn't it 2/3? Okay, when you're raising a power to a power, you multiply the exponents. 2 times 1/3 would be 2/3, right? So there's your y prime squared. Now we add a 1 to that. 1 plus y prime squared is equal to 1 plus 4 9x to the 2/3 power. Want to go on and get that in a rational form rather than a mixed form? Sure we do, don't we? Okay. That would be what? 9x to the 2/3 plus 4 over 9x to the 2/3. Wouldn't it? Yeah, but you just go back, you get 1 over 1 plus blah, blah, blah. Okay. So now we've added 1 to that. Now we've got to take a square root of that. Oh, my word. Oh, my goodness. Let me make sure I am heading in the right direction here. Oh, you know what they did? They reversed their... Wow. They reversed their variables, which I can't see any immediate reason that would have made that intuitively obvious thing to do, but they did. See, what we wound up with is a mess, because now to try to take the square root of that, the denominator is not bad, but the numerator really stinks. And what we would have to do is a substitution, I think probably a trig substitution, or more reasonably, look it up in a table, and even if you could find that in a table, that would be a pretty hairy thing. Sorry, again, took you down a wrong path. They took derivative with respect to y. Now, when you do that, you have to change your interval, okay? So, when x is equal to 0, what is your y equal to? Second? 1, okay? So then on, and this will be the y, that will be from 1 to, when x is equal to 8, what is your y equal to? Well, 8 squared is 64. That thing cubed 64. Take a cube root of 64 and you get 4. So y minus 1 is 4, so y would have to be 5. Okay. The y is on that interval. Okay. Now we will take our derivatives this way, this time I think implicit differentiation does work pretty nicely. This will be 3 times y minus 1 squared is equal to 2, maybe it doesn't. Okay. I guess it's better just to take the square root. I was going to say it might, but I don't think it makes it any easier. So let's start with x is equal to, and we're only going to take the positive square root because they only show the curve on the positive side. That would be y minus 1 to the 3/2 power. Right? Now take dx dy. And what would that equal? What would that derivative be? 3/2 y minus 1 to the 1/2. Okay. There's your dy dx. Next thing we need, so sorry about this, all this stuff up here was for naught, except to show us that it was the wrong way to go. I'll tell you in a minute a conjecture. I'm not sure it will actually be the truth, but at least it might lend itself that way. I don't think we need this either. That was a result of that. So, what's the next thing we're going to do after we get dy dx? Dx dy. And Brendan's here. We're doing example 3, bottom of page 476. Okay? But after we get dx dy, square it. Okay, we're going to square this and square that. Ha! So dx dy squared. The numerical part, similar to before, what did that come up being? 9/4. And what happens when we square that? Oh, how nice. Just y minus 1. I think this is something we might be able to live with. Next thing we do with that is add 1 to it. Okay? So plus 1 here, and we'll do this plus 1. Okay? Let's see what that gives us. This will be 9/4 y minus 9/4 plus 4/4. You okay with that? When we add in fourths, and that would be what? 9/4 y, not that hard, minus 5/4. Okay, that is now that thing. Then the next thing we got to do is take a square root of it. Things are getting worse again. Okay, and that's what we integrate. So we're going to integrate this time, since we're doing dy's, we're going from 1 to 5. I'm going to pull out a 1/2 because that comes out from under the radical and is there, and this is y minus 5, no, 9y minus 5 to the 1/2 power dy. Okay, you okay with that? What I did was pull out the 1/2, so it's out front, leaving this 9y minus 5 under the radical, so it's the 1/2. Believe we can do that as is, right? What would that give us? Or would you like to do a substitution to make it maybe be a little cleaner looking? Which you prefer? Try to do it like this or do a substitution? You tell me. You paid your money. You take your choice. Help me. Substitution? Okay. What would you substitute? Let u, that's our favorite substitution, right, equal the innermost part of your problem, 9y minus 5. Then, what's the next step for the substitution? du is equal to 9 dy. Okay, leave it right there. Justin's here. Good deal. All right. Oops, I just marked you as Ariel. You're not Ariel today, are you? Okay. So this may be an absence. Okay. Ariel didn't come in, did he? By the way, what is this? All Y chromosomes, the story of my life, okay? Yeah, I don't see any X's in here. All right. So there's your du, but we don't really have a 9 dy up here. We have just a dy, so let's divide both sides of that by 9. Okay, so we have dy. All right. Now, if we divide by 9, that pulls it out here and makes a 1 over 18. The d because in here we're going to have a du now, and we had to have a 1/9 dy, so 1/9 du is dy, so that's where that came from. We have to change our limits again. When y was 1, what was your u? 4. When y was 5, what was our u? 40. Okay? And then what is our radical there? That's u to the 1/2. And can we do that integration? It's antiderivative of u to the 1/2. Help me, somebody. Where's the u going to pump up to be? U to the 3/2, add 1 to it, then you have to multiply it to something to give you a 1, so that's going to have to be 2/3, right? 1 over that, which is 2/3. That evaluated from 4 to 40. Which looks like it's really going to stink, okay? Well, one thing I'm going to do is 2 into 18 will be 9, so this is going to be a 1/27th out front. So that's what I'm going to do with my constant, okay? And then I've got to fiddle around with my u to the 40 to the 3/2 power. Well, that would be 4 times 10, and the square root of 4 is 2. 2 cubed is 8. So I think that's going to be 8 times 10 to the 3/2 power, if I'm not mistaken. Okay, minus, and then the square root of 4 is 2 cubed is 8. Alright. I think now this, I'm getting more and more boggled here. I think that's going to be 8/27 times 10 to the 3/2 minus 1. A nice round number, okay? They left it in another form, okay? If someone has a calculator, do this for me. Take 10 to the 3/2 power, subtract 1 from it, and multiply that by 8/27, and see what you get. Hey, look at that, same answer. And that just is illustrative of a different thing. Now, the answer they got in the book before they rounded was 1/27, that part's the same, or sort of the same, times 40 to the 3/2 power minus 4 to the 3/2 power. Now, I think I asked y'all this at the beginning, whether y'all were big fans of things like WebAssign and things like that. Yes or no? Be honest with me. Do you like it or not? Okay. One of the things I mean, I'm not saying it's a bad package. I think it has a lot of tutorial and other things on it that might be very nice and useful. But when you're doing problems like this, they're looking for one answer. If they had written the answer in this form, I'm not sure, I guess I ultimately would have gotten there. But to me, this is not the simplest form. That form is far simpler to me than this one is, because you can obviously evaluate some of this stuff in here. And 10 to the 3/2 power is a lot easier than that. So I never would have gotten, well, I won't say never. having, now I don't know if you get to see their answer or not. I don't know. I want to undo that. Goodness gracious, would you quit? I can't slash my 7. That's a 7. Because there's a hidden thing down here every time we try to slash it. So that's why if you'd have written that answer down, all they just said is wrong, where it's a perfectly good answer. I think better than theirs. And yet they tell you it's wrong. And that drives me nuts, okay? So, especially in calculus, but even in lower level courses, I find it not particularly friendly thing to use. Any questions on that? That's a really complicated, but like I said before, finding functions that when you take the derivative and square it and add 1 to it and take the square root to get something that's even integrable is pretty amazing to do. And that's why they started out with such a weird function as this, and then had a couple of other things you had to do with it, a couple of changes in there. This really turned into a hairy experience. So let's move on to example 4. You okay with it? Anyone need this a little bit longer? Okay. Example 4. Here's another one. And this one actually is at larsoncalculus.com for this type of an example, so you might find it. Find the arc length. Oh, what a fun-looking graph this will be, okay? Y is equal to the log of cosine x. Okay? Now, it says from, and why they write it like this now, I would just write it as an integral, 0 to pi fourths. Now, I would say on that. They started to say from, but okay. Now, is that even legitimate? What is the cosine of 0? 1. Log of 1 is 0. So that's okay. We can handle that. Cosine of pi fourths is something less than 1, right? Root 2 over 2. You can take the log of that. That's okay. Could they have gone to pi halves? No. Why not? Cosine of pi halves is 0. You can't take the log of 0. So that's why it's sort of a weird little interval there, 0 to pi fourths. You couldn't go as far as pi halves. You certainly couldn't get on the other side of pi halves, because then you're in a terrible situation. You go negative and you can't do anything negative, okay? So this is well posed, okay? Everything's defined here. What's the first thing you got to do? Take a derivative. Y prime is equal to what? A little louder. What's y prime? What's the derivative of a log function? A little louder. Derivative of ln. Say again?
The inside and the outside.
Okay, well, yeah, log is the outside. So what's the derivative of the log? I hear 1 over cosine x. So 1 over cosine x times derivative of cosine x, which is it? Negative sine x. Okay. All right, got it. And what's that, by the way? Negative tangent x. So I don't know if that's helpful or not, but you could write negative tangent x if you don't like writing all those other letters, okay? I'm going to clean that up just a little bit because it's hard to see. Okay. Now, what do we got to do with that? square it, so y prime squared will be tangent squared x. Okay, I'll buy that. And then what do we got to do to that? Add 1 to it, so 1 plus that. I'll just put a plus 1 here. And then what do we do with that? Take a square root of it. Okay, and that's going to be your argument, the square root of 1 plus tangent squared x. Now, is that anything we should remember? Yeah. What? It's what? That's secant squared x, isn't it? Okay? Because sine squared plus cosine squared equal 1. And if you divide each of those by cosine squared, you'd have 1 plus, tangent squared plus 1 is equal to secant squared. So this would be, and square root of secant squared would be secant. Okay. So we have the integral from 0 to pi fourths of secant x. Is that right? But, let's see, how do I want to go with this? I don't remember what the antiderivative of secant is. It's not a very simple function, okay? But I do know that secant is, I don't know if it's going to be helpful, but you could write that as cosine x to the minus 1, right? Is that helpful at all? I don't think so. Is it? What's that? The antiderivative of secant is what?
Secant times tangent.
I think the derivative of secant is secant tangent, right? I think you're going in the right direction, though. If you were to multiply numerator and denominator by tangent and proceed from there. But you know, there's an easier way to do this. You want to know what it is? Yes, go to a table. And I don't know where it is in this book. It's got to be somewhere here. Is it in the front? Other books it's in the back. In this book it must be in the... there it is. Derivatives and integral. The integral of secant u du. Okay? See it? Number 12, inside front cover. The ln of secant u plus tangent u. So forget this second part here. That was chasing a rabbit hole. Okay, so let's go back here. This is going to be the log of absolute value secant x plus tangent x. Okay, but guess what? In the first quadrant, these are both positive, so the sum is positive. So we don't need the absolute values, right? Oops, get my eraser up before I erase. Let's just make that a parentheses and evaluate that from 0 to pi fourths. Okay? And what would that be? Secant pi fourths plus tangent pi fourths minus the log of secant 0 tangent plus tangent 0. Okay, I can't read my writing there, but hopefully you can. All right, what is secant of pi fourths? Anyone remember? Square root of 2 plus, what's tangent of pi fourths? 1. Okay. Hard questions there. minus the log of what? Secant of 0. 1 plus and tangent of 0. 0. Okay? So this is beginning to look a lot like log of root 2 plus 1 plus root 2 minus log, what's log of 1? Second? 0, okay. So I could take care of that one. Okay. Well, I thought I could. All right, I think there's our answer. Natural log of 1 plus root 2. Okay? Or root 2 plus 1. Oh, they say, oh, minus 1. Minus log 1. I'm glad they put that in there. And if someone will punch that in the calculator and see if they indeed got it right, what is 1 plus root 2? That's be 2.414 approximately, and the log of that. Is that it? 0.881. Good deal. So that log of 1 there does you absolutely no good. If they would have put that as your, if they would have required that to be the answer in WebAssign or whatever, and counted that wrong, I think I would have shot it. I mean, no questions asked. That's crazy. Okay, so there was example 4. Any questions on that one? And it's not illegal to look it up in the table. Okay, if you don't remember some of the more esoteric things, go to the table. Okay. Save yourself a lot of time. But your idea, if you had multiplied and divided, you'd have gotten there, but it would have been a mess to get there, I think. Well, all right. Let's do example 5. An electric cable is hung between 2 towers that are 200 feet apart, as shown in the figure. The cable takes the shape of a catenary whose equation is y is equal to 75 times e to the x over 150 plus e to the minus x over 150 okay, which is also equal to 150 times the hyperbolic cosine of x over 150. Now, y'all are coming from a variety of different schools, I take it. Did y'all do hyperbolics? Did? Yes? Okay. Frankly, since they're exponential functions, to do hyperbolics without having to look up what the answer is, I'm so afraid they're so similar to sine and cosine, but not quite the same, that I'm going to miss a sign or forget it, something or another. So I have to look them up anyway. If I have to look them up anyway, I can do exponentials without looking them up. So even though it's a little bit longer, I'll leave it in exponential form. But if you like and know and remember your hyperbolics, go for it. Use them. But I've never seen very many advantages to them. Okay. Now, what they do on their graph here is set this up with the lowest part of the catenary. If you picture this, they go from minus 100 to 100 rather than doing 0 to 200. They do minus x going from minus 100 to 100. Don't know if it's any special advantage to that, but you could do it. So what's the first thing you're going to do? So far in this course, though this is usually more for Cal 1, when you ask a question like that, did I say this before? And I know I probably did in your class last time. But so far, it seems like the first question is going to be sort of like, I don't know if any of you go to churches where they have what they call children's church, but if you do, and usually they get all the kids up front, and then some pastor, pretty senior-looking person, goes up, tries to talk real nice to them, and ask them a question. Usually start off with, and most of the time the kids are shell-shocked, and they don't know what to do. So some kid somewhere in the back will usually say, "Yo, this is church. What's a good answer? Jesus, no matter what the question is, no one's going to say that's a bad answer, are they? So usually they can get by with that. Well, in this course, it seems like so far a good answer, whatever I ask, say, take a derivative. Might not be right, but it seems like it's never going to be a bad idea. So first thing to do, take a derivative. And what will that be? 75 times, and what's the first one there? Derivative e to the x over 150. E to the, what'd you say? It's same thing, x over 150, but then you have to chain rule it and do over 150, right? Derivative of x over 150 is 1 over x 150. And then the next one, help me. Minus e to the minus x over 150, and that's also over 150, okay? So that derivative is 75 over 150 is 1/2. Nice, huh? E to the x over 150 minus e to the x minus x over 150, which, if my memory isn't too bad, is 1/2 sinh hyperbolic sine of x over 150, okay? If you prefer that, okay? Which obviously the book doesn't. And then what's the next thing we're going to do? After we take a derivative, square it. So y prime squared will be what? 1/4. And then it's that thing times itself. Okay? So can I just, I know it's not right mathematically, but just multiply this with x, e to the x over 150 times minus e to the minus x over 150. And do anyone see what that's going to do? That would give you what? What's that again? I can't hear. Okay. E to the x over 75, because you're squaring that, which doubles your exponent, which x over 75. Okay. And then if you multiply this times that, what do you get? A minus 1, and this would be another minus 1, so that's going to be minus 2, right? And then the last is going to be a plus e to the negative x over 75, right? By that? All right. And then what are we going to do to that one? Say again? I can't hear.
Simplify.
Okay.
Oh, you've already done that.
No. After you get the y prime squared, what do we do to it? Add 1. Okay? So I'm going to add 4/4. What we, well, actually, maybe we'll take Brandon's advice and simplify a little bit. Okay? I'll make the e to the x over 75 over 4 minus 1/2, right? 1/4 times 2, plus e to the minus x over 75 over 4. Okay? I don't know why I put brackets on it, but I did. Okay, I don't need them. Now, I'm going to add 1 to that, so I'm going to take the brackets off. Okay? Take off that bracket, take off that bracket. I'm going to add 1 to it. But I'm going to add that as 2/2. Is that all right? And when I add 2/2 to a minus 1/2, what do I get? A plus 1/2. So that's going to be what I integrate, right? So we're going to take the integral from minus 100 to 100 of this thing, okay? E to the x. Let me go on and take out my 1/2 again. I mean 1/4 again. I don't like messing around with all that many denominators. So let's take out my 1/4. Ooh. Okay. And that leaves me a e to the x over 75 plus 2 plus e to the minus x over 75 dx. If I'm not mistaken, that's my integral. And can we do something with that? The antiderivative of that, I'm going to put my 1/4 up here out front. Antiderivative of e to the x over 75. Anybody? I love e's. It's so easy to integrate or differentiate. It'll be x over 75. But then we got the sort of unchangeable part, which would be multiplying by 75, right? It's dividing by 1 over 75, I think, isn't it? Yeah. When you take the derivative of that, yeah, that works. Plus, that was this part. This part is 2x. Okay, that was quick. Plus, or a minus, actually, right? Would have been a plus, except that minus up there is going to make that become a 75 e to the minus x over 75. And that's evaluated from minus 100 to 100. Okay? Now, I want to do something else, and I didn't draw the picture because I don't have room for it. But remember I said they were doing this. What you do is, so find the arc length of the cable between the two towers. Okay? I've been setting it up the way they did, minus 100 to 100. But guess what? The arc length on this side is the same as the arc length on that side. So let's just go 2 times 0 to 100. You buy that? Okay. So let's do that. All right. So if I do 2 times 1/4, I get 1/2, and we'll just go 0 to 100. Okay. Hate to do this on you. I started to do it earlier, but I wasn't sure I could get away with it, or hopefully not even need to, but I did. All right, we've got to take the antiderivative of that thing on the inside. This is going to be 1/2 antiderivative of, or didn't we just do that? I'm getting myself totally confused here. No, we didn't. We just squared it, okay. So antiderivative of that would be, or did I? Oh, I did do it up here. I'm sorry. I thought I had. Sorry. I should have done this sooner. Okay. Okay. Make that a 1/2. And we'll just go 0. That was what I was going to do. There's where I was going to do it. Okay. All right. So that's 1/2 times 75 e to the second. 100 over 75 is 4/3. Okay. Minus 200 minus 75 e to the minus 4/3. Okay. But then we've got to subtract. Oh, I'm out of room. I'm going to go and erase this line below it. Is that okay, even though that was an integral part of the problem? I just don't have room for it. I was going to move to the upper side, but I was afraid that would get really confusing, as if this isn't. Okay. All right. That's a 0 up there. Okay. Now we've got to subtract, okay, the 0, and that would be minus 75 when x equals 0. That goes to 0, so we don't have to worry about that. There'll be a plus a 75 here. Well, guess what? That wasn't too bad, because those add to 0. Okay. Now, that supposedly is our answer, okay? And it doesn't look anything close to what they have in the book. Sorry about this. I must have made a really dumb mistake somewhere, because oh, they saw that as a perfect square. Oh, wait, yeah. I did make a really dumb mistake somewhere. We did all that, but then I forgot to take the square root. That was the whole purpose of doing some of this. This is the square root of this thing. And the good news here, this, just like we did on a previous problem, the square root of this is exactly where this was, where this part here was this part minus this part squared. This with the plus 2 in it is this thing plus that squared. So this is, I'm sorry, forget all this, most of this at the end here. That was all. The answer actually gets simpler, believe it or not. If that wasn't simple enough for you, okay, this is, the square root of that thing is this thing with a plus sign in it. So it would be 1/2 the integral 0 to 100. Okay, I don't think they did that in the book, but we are doing it. And that would be e to the x over 75 plus e to the minus x over 75 dx. Okay. And taking the integral of that is 1/2. That would be 75. Wait. No. That's 150, because we have to take half of it. Whereas this was a 150, this is a 150 here too. I didn't I didn't do it there. Okay. Because you see, this gave you 75, then integrating it takes, or square it, so that's 150. Okay. So we integrate that. That's a 150 in front. E to the x over 150 plus, or now that becomes a minus. E to the minus x 150, e to the minus x over 150. And that's what we integrate between 0 and 100. All right. Now what that gives us is 1/2. Well, pull out the 150s, and that gives you a 75. E to the 2/3 minus e to the minus 2/3. Minus 0, which would be, again, a -1, minus a minus, which is a +1. 1, yeah, no, yeah. So I think they go away, and that's what we get. Whoa! They got 150, I got 75. Oh yeah, they... Well, I thought I already had doubled it, but maybe I didn't. Off by a factor of 2, but that's not enough. Anyway, we got in the same ballpark there. I'm not absolutely convinced. Well, I had a 1/4 in there. That's right, I forgot that. When I took the square root, I think I would have lost that. So I think that's where it went. So anyway, I'm not going back through it. Okay, let's call it quits on that. Area, and again, yes.
Can we take a break?
Yeah, let's take a quick break. Good place to take it. Make a dumb mistake early in it, or anywhere along the way, and it really comes back to bite you. That's another reason I like to give take-home tests. Can you imagine doing one of these in an hour test type situation? Well, I turn on the bulb thing and nothing happens. Now it does. Okay. It'll come up here in a minute. No questions so far then. Okay. This sort of seems like we're going to go back to the not too distant past here. We're going to talk about, but it's not quite the same. Before we had an area, we rotated about some axis, and we get a volume. Now we've got a arc length, a line. You rotate that about an axis, and you get a surface of revolution, we call it. Okay? When the graph of a continuous function is revolved around the line, the resulting surface is called the surface of revolution. Okay? The area of a surface of revolution is derived from the formula for the lateral surface area of the frustum of a right circular cone. Oh yeah, okay. That sounds like a lot of fun. So here's what you got. Now, certainly your curves are not going to be all straight lines, but if they were straight lines, and you would have this would be what they call the surface area of the frustum of a cone is chopped off on one or both ends, okay? Where R1 is the radius of the left end, R2 the radius of the right end, okay? Now, this would be the length of that lateral cut, you might say, and then this is what's rotating about the axis of revolution, revolving around the axis of revolution. And what you have then, see if they break it down in a picture, not really, okay? If you picture this going around here, I'm just going to take a little bit in the middle here, going around here, all the way around, the distance that little bit travels is 2 pi times something to do with this radius. If I take it in the middle, it would be exactly the midpoint of R1 and R2, right? So that would be R1 plus R2 over 2. And I'm going to rotate that around. That would be 2 pi times that midpoint portion there. And of course, then integrate that from R1, from this point here where you have the R1 to this point here where you have the R2. And you would have that. But you see, the R is a function of your X. So, when that line segment is revolved around the axis of revolution, that forms this, which is 2 pi R, where R is the average between those two, times L, where L is the length of that lateral cut, you might say. Okay? So, where R is that midpoint radius. Now, we'll just leave it like that for now. So, let's consider a function that has a continuous derivative on the interval from A to B. Okay? The graph of F is revolved about the x-axis to form a surface of revolution as shown. But we're just going to take this little piece here, and that looks like a pretty big piece, but it's this piece blown up here. Well, no, this is the curve. Okay. This is the whole curve here, done around here, and if you take a delta x, you go from A to B, where A is your x1, the x of 0, and x of 1, x2, x of I minus 1, so x of I up to x of n. Okay? And of course, the larger n is, the smaller the delta x is. So the delta x is the difference between x of I minus 1 and x of I. Okay? And if this is indeed the frustum of a cone, then this is just going to be a delta yi, which is going to fit Pythagorean theorem very nicely. Delta x squared plus delta y squared, I is your delta li squared. So it's very similar to what we did before in finding arc length, only we're just going to take the approximation there. But as n gets larger and larger, this gets smaller and smaller, so that segment is going to be closer and closer to the actual surface of revolution. Okay? And if you remember back what it is, 2 pi RL, where R is the midpoint. But of course, if you get these closer and closer together, that R gets to be just the radius at that point here, which is, of course, your functional value at that point there. So what your R is going to become is your F, and the L is going to be this hypotenuse of your right triangle there. Okay? So this is where it's heading. Let delta be a partition of AB with subintervals of length delta x of I, or it looks like a J now. I don't know which it's supposed to be. Then the line segment, delta L sub I, is going to be the square root of delta x of I squared plus x of I. The Pythagorean theorem there generates the frustum of a cone. The r sub I will be the average radius of the frustum, one in the middle. By the intermediate value theorem, a point d sub j, is that I or j? I guess it's I. D sub I exists in the I subinterval such that r sub I is equal to f of d sub I. Well, as I said, that's going to be your function value at that point. The lateral surface area delta S of I of that frustum will then be 2 pi the r sub I, which is going to be your f, okay? Well, they put d's in there, but that's fine, whatever you want to call it. And the delta L is going to be your square root of x of I squared plus y sub I squared. Then we're going to do the same little trick we did before, divide both of these by delta I squared, leaving a 1 plus delta yi over delta xi squared, and pull the delta xi that you divided. When you divide this, you multiply by that 2, and that goes outside. That becomes your dx. This becomes your dy dx squared, 1 plus x. Just like we had before, only 2 pi f. Which, if you think about it, this is the arc length right here, and this arc length 2 pi times the radius, which is your function value. Yeah, that's going to give it to you. 2 pi times the radius, that's going to be the circumference, times the length, the arc length right there. That is your surface area. Now, little s was our arc length, capital S is surface area. Okay? And by this was intermediate value theorem here, mean value theorem there, the number c sub I exists such that that is some derivative. So your delta S sub I then ultimately becomes the derivative at some point c sub I. That leads to a summation here of all those f sub i's with those arc lengths, and that ultimately will lead to the integral. Okay? And frankly, and this of course is the limit, as your del, the delta x value there is approaching 0, it's n approaching infinity. So the delta x becomes a dx, and you've got 2 pi times the radius times the arc length. And frankly, once you identified that at the beginning, jump to it right now, you know, without going through all the summations and the i's and the other things. This, to me, is pretty clear. 2 pi times the radius, which is the function value that you're rotating around. This is when it's rotating around the x-axis. Now, if it's rotating about some other axis, you have to add or subtract to this radius here. But if it's around the x-axis, f of x is that radius, and this is the arc length. So, pretty straightforward, and that's going from x1 from A to B. So in a similar manner, if the graph is revolved around the y-axis, then it's 2 pi times the x. If it's y is a function of x, if this is going around, and then this is your arc length that way, going around the y-axis. Okay. It would help to have a figure there. I'm not sure they show one. But it works out well the same. Okay. Yeah, here's one perhaps. In these two formulas of S, you can regard the product of 2 pi f of x and 2 pi x as the circumference of circles, okay, traced around a point xy on the graph of f as it revolved around the x-axis or the y-axis. In one case, the radius is your f of x. In the other case, it's just the value x. Okay. So this one is rotated around this way, so you get your Christmas tree stand. Okay. Now you're only interested in the lateral area, not the volume of it. Revolved around this way, you get a different Christmas tree stand. that's done this way. That's what this one is revolved around that. Now that, of course, is what y is equal to f of x. That's almost symmetric in either direction, but not quite. That's why you get something that's very close to the same. So it all depends on your axis of revolution. So, well, here we go again. Yeah. Here's the definition of that area of surface revolution. That y is equal to f of x, it can have a continuous derivative on the interval a to b. If it doesn't, hang it up. You can't do this if you don't have that derivative. Continuous on the interval. The area S of the surface of revolution formed by revolving the graph of f about a horizontal or vertical axis, okay, is then S is equal to 2 pi, interval from a to b, r of x, now that's that radius, and you have to define this depending on your axis. Now this is the x-axis so far because that's the function of x. And then this is your segment of your arc length, okay? So 2 pi times that r of x, or r of x is the distance between the graph of f and whatever your axis of revolution is. The x-axis, that's just f of x. If it's above that, okay, then it's f of x minus that common 7, or whatever it happens to be, okay? If it's up here revolving around this way, it would be that number up there, 13 minus f of x, if it's revolving that way. If it's down here below the x-axis, it would be f of x plus whatever value it is down there, minus a minus, okay? And you can go on from there. If the x is equal to g of y, so they're doing this differently this time, and you're revolving around the vertical axis, and your axis of revolution is then, the radius of that is r of y. If it's a y-axis, then this would just be y. So they changed it before. They had that being x here and leaving it as dx's here. Now they're changing it like we've seen before, some r of y. And again, if you move it, wherever you move it to, you just have to identify what that radius is. It's going to have the g of x somewhere in, g of y somewhere in there. All right. So here's area, this is example 6. And let me go back here. They shortened this in the paragraph or the writing below the definition in your book. And I think this is sort of important here. Remember, I kept saying this is your segment of your arc length. So they changed this to be ds and this to be ds. Of course, that changes your limits here. Okay, but they don't change it at the thing there. Oh, that's interesting that they would do that. Well, if you always go back and put these values in for that, you can leave the limits alone. But that's another way to express this, your radius times your arc length. So it's sort of saying the same thing I was, but a little more concisely perhaps. Okay, example 6. Find the area of the surface formed by revolving the graph of y, f of x equal x cubed on the interval 0 to 1 about the x-axis is shown here. So this is sort of a straightforward one. What you reckon the first thing you're going to do? Find the derivative. F prime of x is equal to 3x squared. Perfect. Okay? Now, how are we going to use that? What's the next thing we're going to do to that? Second? Yeah, we're going to plug it in, but what's the formula going to require us to do with that derivative? Square it. So that thing squared would be 9x to the fourth. Okay, we got that. What's the next thing we're going to do to it? Add 1 to it. Okay? And then the next thing is take a square root of it. Okay. So that's going to give us part of our integral. Okay? Now the part that we don't have is the 2 pi r. Well, what is that here? If this is your dx here, okay, so here's your dx, okay, your radius here is just going to be your f of x. So our integral here is going to go from 0 to 1, and you got a dx out here, because that's what you're going by. Your f of x is going to be your x cubed, and you're going to have in here the square root of, you got the 2 pi out front, 2 pi r, that's what gives you this, and times this arc length part, the square root of 9x fourth plus 1. Now, I know that a couple of you, 3 of you, 4 of you, were in my class and we didn't get as far as substitution last time. But we've already substituted a time or two. This problem is set up perfectly for substitution. Okay? And what do we usually use as our substituting element? The innermost part of your most complicated looking part. And what would you say the more complicated looking part of your integrand there? It's going to be the radical. The innermost part of that is going to be that. So let's that be our substitution element. So and most of the time the favorite name for that is u. You can name it anything you want to, but not x, y, or pi or something like that. Let it be something else. So let u equal 9x to the fourth plus 1. Okay? Now, next step is always then what's next? Once you set that part, you're trying to get to a d part. So the du is equal to what? 36x to the cubed. Okay? 36x to the cubed dx. Okay, write it in differential form, because that's how we have it up here. Okay? Now, if you notice what we got down here as opposed to up here, you have an x cubed dx up here. Well, here we have x cubed dx. We don't want the 36 as part of that, so let's divide both sides of this by 36. Divided by 36. Therefore, we lose that. So now, our x cubed dx is going to be our du over 36. So we can pull the 1 over 36 out here, and that will be good. And let's see what we've got there. Bringing the 1 over 36 out with the 2 pi, that would be 1 or pi over 18, right? Everybody buy that? Okay, times the integral from 0 to, oh, whoa. If we're changing our variable here from the x's, we have to change our limits to u's. So when x is equal to 0, what is u? 1. Okay, so this one up here is going to be 1. Okay, and when x is 1 here, what is your u? 10. Okay, so we're going 1 to 10 when you're doing your du's. Okay, now the x cubed dx, that became the du with the 1 over 36 out in front. Okay, that's done. So that's taken care of. So what we have here is the square root of u. Whoa, that's an integral I might be able to do. Especially pi over 18, integral from 1 to 10. If I rewrite that not in radical notation, but in exponential notation, what would that be? U to the 1/2 du. Hey, I think I can handle that one. That's pi 18ths times, what's the antiderivative of u to the 1/2? U to the, louder? 3/2. And what coefficient will I need then? 2/3. Okay? Evaluate it from 1 to 10. Sorry. I keep wanting to put 0 to 1. Okay. 1 to 10. Okay? I prefer having a 0 there, but I don't. So I'm going to pull the 2/3 out front because that's going to be multiplied by everything. So 2 will go into 18 9 times. So this will be pi over 27 times, oh boy, not going to get very pretty here, 10 to the 3/2 power minus 1 to the 3/2 power, and that's going to be just 1. Okay, unfortunately, I don't know what the square root of 10 cubed is, but it's just a number. And let's see if that's what they got in the book. Pi 27ths times 10 to the 3/2 power minus 1. And if you punch that in the calculator, hopefully you'll get the same thing they did, something around 3, a little more than 3.5. 3.563 or so. I don't know if you did it or not. Does that make sense? Okay. And again, you've got to have a function that when you take its derivative and square it and add 1 to it and take a square root of it, you got something you can integrate. Okay. This was helped by the fact that the function itself was that, and well, no, the derivative was that. Let's see. No, the radius was that. So yeah, that did come out being something we could manage with substitution, of course. And let's see, let's watch how they did it. See if they did anything any differently. All right. They started off with writing down their formula, and we didn't write down the formula to begin with. We started doing the pieces to it. But the surface area is 2 pi times the radius times the arc length interval, okay? And the radius in this case was just a functional value, f of x, which was x cubed, okay? The derivative of x cubed, 3x squared, when you squared that, 9x to the 4th, plus 1, take the square root of that. The good news is that came out being, and here's what the deal is with this. Well, they haven't squared it yet. They're going to. I don't know. Yeah, okay. This is fine. So they've written this in this way with okay. It's obvious if you look backwards why they did this, but it's not obvious from a progressive point of view going forward why they multiplied and divided by 36. We know they had to, so they could get this, okay? But they just have gotten that, and so they do their substitution with a crystal ball. They look ahead and see what they're looking for and then get that over here. I do it as I come to it and then pull out anything that doesn't give you what you need out here. So it works out the same way. But the substitution part of it is that this is one more power than this, so that leads you to think if you take a derivative of this, you can get it to something that looks like this dx. That's the key to the substitution, that you get on the outside the derivative of what's on the inside. It's an undoing a chain rule type thing. Okay? Now, this became pi 18ths, and they did their integration just like we did. Now notice here, they didn't do a substitution. They left it all in the x's, saw that that's panning out okay, so it's okay to do it that way. It just seems like to me, most of the time, people see the substitution a little bit easier. But they're going from 0 to 1. And the maybe, hopefully not surprising thing is, and rather than writing over 3 over 2, why don't you write it 2/3? And then you can cancel things out. But anyway, with magic, they come up with this, and that's the same thing we got. Okay? To me, they're jumping lots of steps there. Whereas if you do the substitution, it's a lot, to me, more obvious what you're doing. But same answer we got, which is about 3.563. All right, I think that's the last slide, but there's one more example, so let's back up and do that example. 7. Okay? The area of a surface of revolution, same thing we've been doing. Find the area of the surface formed by revolving the graph of f of x is equal to fx squared. So f of x equal x squared, good old parabola, on the interval 0 to root 2, okay, about the y-axis as shown in the figure. So you look at the figure, I don't really want to draw it, but you got half a parabola, 0 to I have the square root of 2 on x, and when you plug that in, that would be 0 to 2 on y. Okay, you see that. Revolve that around the y-axis, and you get a portion of a paraboloid. Okay, though you haven't gotten what those are yet. Okay. Now, the question is, we're looking for the surface, the area of the surface area, the capital S. Now, since you're revolving around the y-axis, way back at the beginning, not way back, but earlier in this time, they gave you one way to do it using the x's, and then they later gave you another way to do it using the g of y. And you can do it either way. If you did it the other way, g of y is equal to take the square root of both sides, and this would be y is equal to the square root of x. X is equal. This is y is equal to x squared. X is equal to the square root of y. Okay. So you could do it that way, or you could do it the way they suggested at first and just have your x there and go around that way. And this one will work well either way. Let me, nope. That's the way they're going to do it. Leave it in dx's, okay? This is going to be hard to do without a picture, so let's draw the picture. I'm not going to draw it and this is revolved around like this. So you get a pointed bowl, not a sharp point, but a pointed bowl. And you're going this is 0, the square root of 2, which up here is going to 2. But if we're not going that way, we're going, so let's do our surface area. It's going to be 2 pi times the radius. And we're going 0 to root 2 because we're doing the dx's here. So this is a dx. Be sure you identify that once you've chosen that. Your radius now is your x. Wherever you are on x, this is the part that you're revolving around. That's your radius, x. Now your arc length part, that stays the same. That's going to be the square root of what? 1 plus f prime squared. Okay? So what do we got to do first? Take the derivative. F prime of x is equal to 2x. Okay? And then what do we do with that? Square it. And that would be 4x squared. And then we do what to it? Add 1 to it. And then we take a derivative of it. I mean a square root of it. Duh. Okay? So that's what's going to go in here. Okay? So this is going to be 2 pi times the integral from 0 to square root of 2 x times the square root of 1 plus 4x squared dx. Okay? And what way do you want to approach this?
Why is it dx then?
Why dx?
Yeah, because I thought, oh yeah.
Okay. If you did dy's, if you were going to choose that way, then you have to write this as g of y would be the square root of y. You know, of x equals the square root of y. And this is y is equal to x squared, x equals square root of y, so you would have to use that. Then you would use the square root of y here, and then you would use your, take that g, not f, and take the derivative of that, and you go through. It works out the same. This way is even easier because you're taking that same arc length, which you can leave either in terms of dx's or dy's. It's the same thing that you're revolving around there, and that your radius here is just the x value. So that actually makes the whole problem a little bit simpler. Okay. You get the same answer. And it won't be a lot more difficult, but it would be a little bit more so. This one, so far, is doing pretty nicely. Where do you go from here? What would you choose to do? Okay, and can you do that pretty easily in your head? I can't either, okay? So what would you do to sort of help simplify the picture? Substitution, what would you substitute? And again, take the innermost part of the most complicated looking part, and that would be there, let u equal 1 plus 4x squared. Then, what do you do next? du is equal to, what's that say? 8x dx, write it in differential form. Okay? Well, here you have your x dx, so to get it to that, divide both sides by 8. So now and you also have to change your limits. When x is 0, what's u? 1. Okay. The 2 pi is out front. I just left that 2 there. Okay. All right. And when x is equal to square root of 2, that would be 2 times, so yeah, that would be 9. Okay? All right. And the du, or x dx is 1/8 du, so you divide by 8. Okay? du is 1/8 dx, and that would be x dx left here. And here we have, and I'd like to go on and write it in exponential notation there, u to the 1/2. I don't even need the parentheses there, do I? u to the 1/2. Do you see that? I, too, have skipped a few steps, but it's not that thing. This right here is your u, so it's the square root of u, and the square root of u is u to the 1/2. All right, I think we can do that integration. First, I'll change this to pi fourths. What's the antiderivative of u to the 1/2? Second? Oh, wait. U to the 3/2, so your coefficient is 2/3. And again, let's go on and get rid of this. So that would be pi 6. Okay. And then we're going to evaluate u to the 3/2 from 1 to 9. Okay. Now, I haven't said this because I was just assuming that everybody's on the same page here. When I'm doing that kind of evaluation, if possible, I always want to take the square root first and then raise it to the power. If you do the power first and then take the square root, you got a huge number. Take the square root first, okay? So the square root of 9 is 3 cubed is 27. So that'll be a 27 here. Minus, when you put a 1 in there, I think I can do that. 1, okay. 27 minus 1, which is very close to 26. So that would be pi 6 times 26, which would be 13 pi over 3, I think. Okay, if I got it right. 13 pi over 3, which is approximately 13.614. Okay. You see how that works?
You said it's a 6 that it's raised to?
What's that again?
27 minus 1 raised to the 6.
It's 27 minus 1.
What's that?
That was my, what was
that?
that? That was something on, I don't know what that was from. Oh, I don't know. I think it was something I had scribbled down here. I don't know what, from my axis. But it's just 27 minus 1. 26. All right. Okay. That finishes 7.4. Let me give you a few homework exercises in that. Do number 5. Any of the odds 7 through 19. There's a whole bunch of them. By the way, all the odd numbers are calcchat.com. Okay. All the odd numbers, number 1, have answers in the back. So try to work them. See if you get the answers in the back. If you can't get it in the back and can't figure out why you didn't get it, then go to calcchat.com. They have tutorial help there and worked out solutions for those odd number exercises. Then for some, like number 7, they have at calcview.com, which has even more detail in it. Then on do any of the odds 21 to 29, all those are at CalcChat. None of them are at CalcView, so you'll just have to go by the answers there. Then do number 31. It stands alone. 33 is very similar to one we did in class. 35 is somewhat similar to that. 37, another one. So I would say do any of the odds between 33 and 37. You choose any or all of them. Then do any of the odds between 39 and 43. They're all at CalcChat. 39 is at CalcView. Do either 45 or 47. They're both at CalcChat, but 45 is at CalcView. Then do 49. There's an exploring concepts, which is a little more esoteric, and if you want to look into it, you certainly can. If you want to go on and skip it, that's perfectly fine too, but that's 51, and then you can also look into 53 if you're interested. Then there's a think about it, 55. I would think through that and, sort of work through it. You don't have to get too bogged down with it. Then you have some lateral surface areas. any of those 57 through either 57 or 57 is the lateral surface area of a cone, and 59 is using a sphere. 61 is modeling data. 63 is volume and surface area. Do either 65 or 67, or both if you choose. And then a good old suspension bridge, 69, and 71 is the last in that group. Now, we have a few minutes left. Is it worth trying to get started on 7.5? Sorry if we lost too much time today. I got started late, and then we had to take a break in the middle and a few dead times in between. So we'll do 7.5, start that next time. It's a fairly short section. Hopefully we'll get through that quickly. Skip 7.6, may do a quick slideshow of it, and then we'll do 7.7, and at the end of that we're through with the chapter and we'll have the test. Okay. When do you want to get together? Right now?
You have another class?
I don't have another class today, so anytime between now and 6 would be good. Do you need it right now, or are you? Okay. Let me go on and get things shut down, then we'll go. Yes, sir.
I missed last Wednesday because I got called into work. Is the video on?
Yeah, it should be. Yeah.
Okay, thank you.
All right. I'll get with you in a minute. Let me get this shut down. Otherwise,